In this video, we are going to solve some problems on chemical thermodynamics. And the first problem is the standard enthalpies of formation of methane, carbon dioxide and water are minus 74.85, minus 393.5 and minus 286 kilojoule per mole respectively. Calculate the enthalpy of combustion of methane. And you know, enthalpy of combustion, it is the enthalpy change associated with or accompanied by a chemical reaction when 1 mole of substance is completely burnt in excess of oxygen. It is called as enthalpy of combustion. And this enthalpy of combustion, it is calculated from the enthalpy of formation. So enthalpy of formation of these three substances are given: methane, carbon dioxide and water. And what is asked? Enthalpy of combustion of methane we are going to find out. This is the chemical equation. Methane, when burnt in excess of oxygen, that is 1 mole of methane when reacts with 2 moles of oxygen, there is a formation of carbon dioxide and 2 moles of water. Now heat of reaction or enthalpy of combustion, it is equal to sum of enthalpies of formation of products minus sum of enthalpies of formation of reactants. Actually, this chemical equation, it is the equation of combustion of methane. Here methane undergoes combustion and there is a formation of carbon dioxide and water, and during this reaction there is a formation of carbon dioxide and water. Okay, now we are using this relation, that is enthalpy of combustion of this reaction, it is equal to sum of enthalpies of formation of products minus sum of enthalpies of formation of reactants. So this is equal to enthalpy of formation of carbon dioxide plus 2 into enthalpy of formation of water. Why this 2 is taken? Because coefficient for water is 2 moles of water is formed, minus, so carbon dioxide and water, these are the products, minus enthalpy of formation of methane plus 2 into enthalpy of formation of oxygen. So again, for oxygen coefficient is 2 and methane and oxygen, these are the reactants. Now all these values are given: enthalpy of formation of carbon dioxide, water, methane, all are given. So just you substitute the values, and enthalpy of formation of oxygen is considered as 0 because enthalpy of formation of or standard enthalpy of formation of elements in standard state or pure element, it is always 0. Oxygen is a pure substance, pure element. Okay, pure element in standard state, and therefore its enthalpy is considered as 0. So when you substitute the values, then answer is minus 890.65 kilojoule per mole. So this is the enthalpy of combustion of methane. Second example, 1 mole of an ideal gas is compressed from 500 cubic centimeter against a constant pressure of 1.126 into 10⁵ Pascal. The work involved in the process is 36.5 joule. Calculate the final volume. Now what is given here? Number of moles are given. 1 mole of ideal gas is there. Then initial volume is also given. Initial volume, it is 500 cubic centimeter. It means 5 into 10⁻⁴ cubic meter. Actually 1 cubic centimeter, it is equal to 1 into 10⁻⁶ cubic meter. So 500 cubic centimeter, it is equal to 500 into 10 raised to minus 6 cubic meter, or 5 into 10 raised to minus 4 cubic meter. Then external pressure is given, it is 1.216 into 10 raised to 5 Pascal. Then work involved in the process is given, it is positive, means work done by the surrounding on the system, or it's a compression type of work, 36.5 joules. Just we have to find out the final volume, that is V2. And the formula is, W is equal to minus P external into delta V, or it is equal to minus P external into V2 minus V1. Delta V means V2 minus V1. So it means it is equal to P external into V1 minus V2. So because of this minus sign, so sign of V2 and V1, they will be reversed, and therefore P external into V1 minus V2. Now when we substitute the value of P external and V1, then we get, now value of work is 36.5 joule equal to 1.2 into 1.216 into 10 raised to 5 Pascal. This is the external pressure. 5 into 10 raised to minus 4, this is the initial volume, minus V2. So just we solve this and we get the answer. So just by rearranging terms, then we get 5 into 10 raised to minus 4 cubic meter minus V2 equal to 36.5 upon 1.216 into 10 raised to 5. This is the pressure. So just we cancel the units, and then we get 30.01 into 10 raised to minus 5 cubic meter. Again by rearranging terms, this V2, it is equal to 5 into 10 raised to minus 4 minus 30.01 into 10 raised to minus 5 cubic meter. Again by simplifying, we get V2 is equal to 20 into 10 raised to minus 5 cubic meter, or this is equal to 200 cubic centimeter. 200 cubic centimeter. Already I told you 1 cubic centimeter equal to 10 raised to minus 6 cubic meter, and therefore 20 into 10 raised to minus 5 cubic meter, it is equal to 200 cubic centimeter. Now next example, calculate the work done in the following reaction. This is the reaction, the oxidation of 1 mole of sulfur dioxide at 50 degrees centigrade. So calculate the work done in the following reaction and state whether work is done on the system or by the system. And the reaction is the oxidation of 1 mole of sulfur dioxide at 50 degrees centigrade. Now temperature is given, so T is equal to, so temperature in degrees centigrade is given, it is 50 degrees centigrade. In Kelvin, just you add 273 in this 50 degrees centigrade, then you will get 323 Kelvin. The chemical equation for oxidation of sulfur dioxide is, sulfur dioxide combines with oxygen. Oxygen is the oxidizing agent, and sulfur dioxide gets oxidized into sulfur trioxide. But here oxidation of 1 mole of SO2 is given at 50 degrees centigrade. Then just to divide each of these term by 2, then we get SO2 plus half O2 gives SO3. So it meaning of this is 1 mole of sulfur dioxide combines with half moles of oxygen, and there is a formation of 1 mole of sulfur trioxide. And for this equation, we are going to find out the work done during this conversion. Okay, now number of moles for this equation is delta n is equal to n2 minus n1, where n2 is number of moles of gaseous products, n1 is number of moles of gaseous reactants. For gaseous product, number of mole is 1, and for gaseous reactant, here 1 mole of sulfur dioxide combines with half mole of oxygen, and both are gases, and therefore 1 plus half, that is 1.5. So number of moles of gaseous reactant 1.5. So 1 minus 1.5, it is minus 0.5. So delta n is minus 0.5. Now we know the equation for gases. W is equal to minus delta n RT. Actually W is equal to minus P delta V, but P delta V is equal to delta n RT, and this W is equal to minus delta nRT. This is used for gases. So just when we substitute the values, then delta n is equal to delta n is minus 0.5, R is 8.314, and T is 323. Then it is equal to 0.5 into 8.314 into 323. So W is equal to plus 1343 joules. Now as work is positive, we can say that work is done on the system by the surrounding. So this is about the work done when there is oxidation of 1 mole of sulfur dioxide. And the last problem number 4, the heat of combustion of gaseous methane at a constant volume is measured in Bum calorimeter at 298 Kelvin, and it is found to be minus 885.4 kilojoule per mole. Find the value of enthalpy change. So this is the chemical equation. CH4 gas, that is methane gas, combines with 2 moles of oxygen gas, gives carbon dioxide gas plus 2 moles of water liquid. So this is the equation of combustion of methane. Now these are the given things. Change in internal energy is given. It is minus 885.4 kilojoule. In joule it will be minus 885,400 joules per mole. Delta n for this reaction is number of moles of gaseous product is 1. Here 1 mole of carbon dioxide is there. Water is liquid, and there are 3 moles of reactants. So 1 minus 3, that is minus 2. Temperature is given 298 Kelvin. Value of R is also given 8.314 joule per mole per Kelvin. And the relation is delta H is equal to delta U plus delta nRT, where delta H is enthalpy change, delta U is change in internal energy, delta N is difference between number of moles of gaseous products and reactants, R is gas constant, T is absolute temperature. Just to substitute the values, value of change in internal energy is given. It is minus 885,400. It is in joules. Delta N is 2 minus 2 into value of gas constant R is given 8.314, and temperature is 298 Kelvin. So after simplification we get the answer minus 890,355 joules, which is equal to minus 890.35 kilojoule. So this is the enthalpy change for the combustion of methane.